right, so welcome to Math 408. This is lecture 9. It is not Mountain Day, so greater chance on next Friday of having no class because of that. There will be something happening, not quite sure exactly what yet. We're going to continue with interpolation. And so, not surprisingly, like many problems in mathematics, depending on how things are formulated, depending on what information you're given, you will have different forms of the answer, and some forms will be more convenient than the other. Let's recall quadratics. So can someone give me a quadratic, a nice generic quadratic? How might you write it?
X squared plus 3x plus 4.
Okay. X squared plus 3x plus 4. I'll put a negative 8 there just to have something everywhere. So this is the standard way you've learned to see quadratics. Ax squared plus bx plus c. If you set that equal to 0, it gives you x is negative b plus minus square root b squared minus 4ac over 2a. And the way you find this is the method of completing the square. There's other ways to give quadratics. I could write the quadratic as a x minus h squared plus k. And again, I still have 3 parameters just as before. This is far more convenient for plotting. When you look at this, where is the vertex? Vertex is hk. And then if you want to solve, it's just going to be h plus or minus the square root of k over a. So for a lot of purposes, this is a more convenient form of the quadratic to look at. So what we did last time, we had points x1, y1 through xn, yn. And we got a polynomial of degree n minus 1. And we could write it as the sum, say, k goes from 1 to n of yk lk of x. And what's nice is lk of x equals 0 if x equals xl when L does not equal k, and equals 1 if x equals xk. So this is a beautiful function for us. It's 1 at the point xk, and it's 0 everywhere else. And so we can just piece together the function from that. All right, so building on this success, one of the ways of proceeding is maybe it's expensive to look at more and more points. So rather than looking at a lot of points, it might be better to look at a fewer number of points, but look more deeply at what is going on there. So instead of just looking at the value of the function at a point, what might you look at? Derivative. So maybe we have x1, y1, xn, yn, and x1, y1 prime, xn, yn prime, with yk, f of xk, and yk prime, f prime of xk. And then the idea is to construct a polynomial of degree 2n minus 1 using this data. So your assignment was to think a little bit about this for today's class. How might you start getting some intuition about this? What should be your first thought?
You might think
Okay, so one thing is to think about what happens when you take derivatives of polynomials.
Yeah.
But I claim that this should be something that you should be thinking about to try to gain some intuition about this problem. What should you do first?
Low degrees.
No, low degrees. In fact, which degree should you do first?
One.
N equals 1. Now, the problem is sometimes when you look at things of low degree, the behavior is completely different and does not really give you a sense of what's going on. This happens in a lot of topology problems. But let's start there and try n equals 1. So we have x1, y1, and x1, y1 prime, and we want f of x is a1x plus a0. And unfortunately, this might be so simple that we're not really going to be able to do much. Is this how you want to write the function? We're trying to do polynomial degree 2. This seems the most natural thing to try. So we would get y1 is a1 x1 plus a0. y1 prime would just become a1. Well, this isn't too bad. Right? This will immediately tell us a1 is y1 prime, so a0 is going to be y1 minus y1 prime x1. And so if we write this out, we would now get y is a1, so it's going to be y1 prime times x plus a0 y1 minus y1 prime x1. So I have deliberately not looked at my colleagues' notes on this problem. Is this a solution? Do you think this is the solution that's going to generalize? Do you want to rewrite this somehow? Yes.
I would write point slope form.
Okay, so how would you write that?
Y minus y1 equals y1 prime times x minus x1.
So I like some of what you've done, but not all of what you've done. Which part? So you've done two things. You put the y1 over here, and you put the x1 with the x. One of them I like, one of them I don't like. Which one is it?
Put the y1 on the other side.
So move the y1 over. So why do I not like the y1 over here? Why do I like the x and the x1 coming together? So if you think about it, we're trying to get something nice at the form, the sum of yk lk of x. And that's going to be a function f of x. If I have more data points, do I keep subtracting multiple y's here? But if I have the x minus x1 together, that's beginning to look like a nice function over here. The difference now is that that function vanishes when x equals x1 and is, okay, well now we only have 1 point, we have 2 pieces of information. So I actually like half of it, and I would put the plus y1 over here. And this might be something that might generalize nicely, except I dropped a prime. It should be, I think, y1 prime. Yes. there's going to be more than one way of getting an answer. What is a little bit different about this expansion than the expansion we had over there?
There's no denominator.
What do you mean by no denominator?
Oh, never mind. Yeah.
There is a difference. What can you tell me about all the LKs over here?
They're all completely factored.
They're factored. And they're all of degree n minus 1. So when we're doing it like this, all of the terms are in some sense comparable. Here, this is not necessarily comparable. This is a higher degree than that. So we might actually like this expansion, and we might decide later that we don't like this expansion, that we would like a different expansion where we have two terms of equal size, of equal degree. But this is not a bad thing to start with, and it's not bad to just look at the simplest case and see, can we build some intuition? And so now that we have that, let's look at maybe degree 4. And so try to think about how we might want to do that. Yes?
Yeah, what do you have there for the sum LKs? I couldn't really read it, and I don't really know what we have.
Right here?
Yeah.
LK of x is equal to 0 if x equals xl when L is not k, and it's 1 if x equals xk. So these were functions that were basically like x minus x1, x minus x2, dot, 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 x minus xk minus 1, x minus xk plus 1, and then they had a denominator, and things were set up so it worked out very nicely. So we were able to do that without too much trouble. I think it was something like LK of x was x minus x1, dot, 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 x minus xk minus 1, x minus xk plus 1, x minus xn. And then the denominator was xk minus x1, dot, 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 xk minus xn. So when you plug in x equals xk, you get 1. And when you plug in anything else for x, if it's any of the other special points, it just becomes 0. And they all have the same degree, so they're all of comparable size. So the question is,
Why did we want that behavior for xk?
part of it was just this was a really nice, simple way to come up with a formula for the polynomial given the data, xk, yk. We have these nice polynomials which in some sense become our basis elements, and this is how much we magnify each one by. So it's a really simple formula for any sequence of points I give you. As long as the x's are distinct, I just look at this combination. And so this allows us to explicitly write down a polynomial of degree n minus 1 that goes to all of these points. This does not mean that there is not another way of writing down this polynomial. One of my favorite stories is there was a lot of work before Newton came up with his law of universal gravity. One of the big pillars that his work was built on was work of Kepler. And you might hear of Kepler's 3 laws. Planets travel in elliptical orbits about the sun, where the sun is one of the foci. And Kepler had great access to data through Tycho Brahe. And this is following the Copernican revolution, where they moved the center of the solar system from the Earth more towards the sun. And so now the planets are going around the sun. And when Kepler was trying to understand the orbit of Mars, he actually had an equation that described it. And he was sad because, it's not an ellipse. It would be wonderful if it was an ellipse. It turns out he wrote down the equation of an ellipse but it was a non-standard way of writing down the equation of the ellipse, and he didn't recognize that he had an ellipse in front of him. I read this in the book, I think it's called like Sleepwalkers or something like that. You know, trying to understand the cosmos. And just absolutely wonderful that he had it right there. But because it was written in a different way, he didn't notice what he had. So part of it is, you know, can you find something that's easy to compute with? These L's are very easy to write down. We're not solving determinants, we're not doing Cramer's rule or anything like that. This has all in some sense been done for us now. So the question now is we have x1, y1, x2, y2, x1, y1 prime, x2, y2 prime, and we want f of x is ax cubed plus bx squared plus cx plus d. So there's a couple of ways we can try to do this. You know, I do have on the board our analysis of the degree 2 case. We can start trying to write down equations. So we would have y1 is a x1 cubed plus b x1 squared plus cx1 plus d. y2 is a x2 cubed plus b x2 squared plus c x2 plus d. y1 prime is 3a x1 squared plus 2b x1 plus c. And y2 prime is 3a x2 squared plus 2b x2 plus c. And if you could figure out why I keep switching back and forth between different ways of writing y, I would love to know. We have 4 equations and 4 unknowns, right? This should be solvable. But when you look at this, is it clear how to try to solve it? Or is it fundamentally different from what we had a moment ago? I mean, if we subtract these two, we can cancel the d's and get something involving a, b, and c. If we subtract these two, we can get something involving a and b. We can replace b in terms of a, and we would have an equation involving b, b, and c. This is getting ugly. So any thoughts about how we might want to proceed?
Could we try the same approach as Lagrange did, like write as a sum of 2 functions, where, for example, the first one satisfies the x, where the first function satisfies the
So 2 functions or 4 functions? When you look at what we did for the polynomial of degree 2, we're actually writing it as a sum of 2 functions. They're not of the same degree, but we're writing it as a sum of 2 functions. One of them is almost like, if you look at this, and you look at this, oh, what is this function giving us? So what is the contribution from this one?
First point.
Yeah, it gives you the first point. This gives you the point information. And when you plug in x equals x1, this is 0, it doesn't contribute. What does this piece over here give you? Right, but
Well, the first derivative.
the derivative. And when you plug in, when you take the derivative, this piece doesn't contribute at all. So we actually have something here that is nice in terms of this part is giving us the point, this part is giving us the derivative. Maybe we can generalize that. Now, my colleague who does sphere packing professionally is not going to be thrilled with this generalization. But it's not a bad first one to try. And then we can tweak it a little bit. But I want to try to motivate how you get to certain formulas. Sometimes cases are so simple that they really can't give you much information. But other times, if you look at them the right way, and so we could leave it as y1 prime x plus y1 minus y1 prime x1. If we do it like that, things are all mingled together, and when we take x equals x1, it's only after we do the calculation that everything cancels and it comes out as y1. If we rewrite it like this, now it's much clearer. Okay, so now, do we agree that this is probably not a good way to go? So I'm going to consign this to hell. It is gone. And so we're looking for f of x is ax cubed plus bx squared plus cx plus c. Do you think if we can do this case that we should be able to do degree 6 without any trouble?
Yeah.
Yeah, I think if we can get over this hump and do the quartic, we'll already have two different points in play at the same time. When you're looking at the linear, when you just have a line, there's only one point in play, so we can't really see the interactions. So I think if we're able to solve this, we're going to be golden. So maybe we'll guess f of x is the sum k equals 1 to 2. And now we're going to have to put in some information. So maybe we'll write it as alpha k a k of x plus beta k bk of x. And this is trying to generalize what we have for the line. And we will not necessarily have a and b of the same degree. So if this is our function f, then f prime of x will be the sum, k goes from 1 to 2, alpha k ak prime of x plus beta k b prime k of x. And now we have to try to figure out what do we want to take for the a and the b. So when we looked at what we had before, the b was giving us the value of the function at the point, and the a was giving us the derivative. Is that the order you want to write them in? Doesn't really matter. So we will have, this is hopefully the point, and this is hopefully the derivative. So what might you want bk to be?
YK.
Well, we can have some of that coming in with the beta,
Oh, sorry.
right? We need bk to be something. It's a function of x1 and x2. So let's start making a wish list. Can I erase the stuff from last time? So wish list. What would you like bk of xk to be? 1.
Yeah.
And then bk of xl would be 0. And we'll always assume L is never k. What about the derivative? What should b prime of xk equal 0. And bk prime of xl should be 0. So again, we're just trying to see, here's our wish list. We had an expansion that worked well in the past. Can we come up with a function that satisfies this? So it's got to vanish. What does this tell you is going on at the point xl? Has a double root. So double root at xl. Okay, what are you starting to think about now?
X minus XL squared.
Yeah, x minus xl squared. If you want for definiteness, maybe make k equal 1 and just try to handle what's going on at that one. And then what should we divide this by? So this would actually now just be x2.
Xk minus x1 squared.
Well,
x1
x1 minus
minus
x2 squared. And now if I take this from my b1 of x, when I plug in x equals x1, I get 1. When I plug in x2, I get 0. If I take the derivative, because this is a double root, this is fine. If we had more than just x1 and x2, would this be generalizable easily?
Yes, but you still don't have b prime of x1 is equal to 0. That's the hard part.
Okay. So we don't have that. So what would we need to do?
We need the derivative to have an x minus x1 term in it.
Right, so the derivative would need an x minus x1 term. But if there's an x minus x1 term, what's going to happen when we don't take the derivative? It's going to vanish. So we can't have an x minus x1 term. So we're able to get 3 out of 4, but we can't get, unfortunately, this one over here. I'm sorry, no, I'm sorry. That's not the one we can't get. Sorry. This is the one we can't get. Okay. But 3 out of 4. Any Meatloaf fans here? The musician? He has a nice song, 2 out of 3 ain't bad. So this is 3 out of 4, 75%. What this is telling us is maybe we can keep this, but at the cost of changing a. So this is good. It's going to give us a b1 of x1 is 1. B1 of any other one is going to be 0. The derivative at any point other than that is 0. But we miss this one over here. And we could extend this to more things. We could extend it to, x minus x2 squared dot 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 x minus xn squared over x1 minus x2 squared x minus xn squared. So it's not hard to generalize this to get something that's going to work everywhere, but the third condition. So what this tells us is that when we do our wish list for A, our wish list for A is going to have to not only take into account what we might want to be happening for the value of the function. No, this is going for the value of the function. We might not only be taking into account the derivative of the function, but also a little bit of the value of the function. No, I'm flipping this, sorry. This is giving us the value of the function perfectly, but it's screwing up the derivative. So maybe that means when we look at A is supposed to not give us anything for the value of the function because B is taking care of that. But A can't be just the derivative of the function. It's got to fix this a little bit.
Can't you just adjust alpha k?
So we might have to adjust alpha k a little bit.
It's going to vanish.
Right, because now when we plug in what's going on at x1, when we take the derivative, it's going to just be some nightmare. But it's just going to be a number. So we should be able to adjust the alpha. So it's not going to be as nice of a formula as what we had before, where we just had the sum of the yk, lk. The alpha and the beta. Wouldn't it be wonderful if alpha and beta were just the y's and the y primes? Maybe there's a way to do that at the cost of a more complicated function. And before we see the solution that people use, I wanted to just try to go through this and see what we would get. All right. I'm going to not erase that. I'll move this up here and try to just use the blackboard so that we can pull it back down if needed. We now need to look at the wish list for the A's. And again, we'll do A1 of x. The hope is that if we can do A1 of x, we can do all of them. So we have A1 of x1. We have A1 of xl. We have A prime of x1 and A1 prime of xl. So what do we want A1 of x1 to be? We want that to be 0 because the b is already giving us what we need. What about the A1 of xl? Also 0 because we've already got what we want for that. A1 prime of x1, let's hold off on that for now. A1 prime of xl should also be 0. Okay, well, if we look at this, what is this telling us in terms of the shape? And here, we're going to have a determined constant. So what should we actually have that value be?
Beta k, or we need alpha k too.
Right, so we can adjust things by alpha and rescale. So what should we have for the value of this constant? Yeah, it should just be 1. And thank you for using that finger. I had a friend in grad school who did have his middle finger in a splint, and it was interesting when he accidentally raised his hand to ask some questions of some senior faculty. So we might as well aim for something like this, because as long as this is 1, we can choose the alpha k to be whatever we need maybe to match things. So when you look at this, what does this give you in terms of what A1 should look like? And we can get the constants off a little bit, but I care about the functional form, how it looks like in terms of x's and x1s and x2s and all that.
Basically the same as b, but like you multiply by x minus x1.
Yeah, so let's just try like x minus x1. And it really is, I think, just the same, just maybe b1 of x. Or just writing out explicitly, x minus x1. And then in this case, it would be x minus x2 squared, x minus xn squared over x1 minus x2 squared x1 minus xn squared. And so when we put in x2 through xn, it vanishes. When we put in x1, it vanishes. When we take the derivative and evaluate it at anything other than x1, because these are all squares, it's going to vanish. When we take the derivative and evaluate it at x1, the only term that survives is when the derivative hits this, and then we're left with 1. So now we can satisfy all of those conditions. And so the only condition that we're missing is, we wanted b1 prime of x1 to be 0. It's not. So we can jiggle things a little bit with alpha. So let's try f of x is the sum k equals 1 to n. We're going to have alpha, so I'm going to try to leave a little bit of space. A k of x plus beta k. So what do we want beta k to be? Yk, because it's going to be our value. Yk bk of x. And because this vanishes at all the x's, it can't change the value of the function. So this is going to give us the correct values for the endpoints. Now the only issue is the derivative. So when we take the derivative, we're going to get, ak prime at x1 or xk, which is just 1. So it's going to be looking like, alpha k times 1 plus beta k. Well, beta is just yk. And now we have bk prime, which is just some constant. It's just bk prime at xk. That's just some number. Even if it's 0, it's still just some number. And we want this to equal yk prime. So that tells us, well, we can solve for ak, because the coefficient in front of ak is 1. So it's just going to be yk prime minus yk bk prime of xk. Okay. So let's see if we can actually still show both of them. So this looks a lot like what we had before. And the derivative piece does look a little bit different. So in terms of just how we're writing it, it's not quite the same.
Well, last time bk prime was constantly 0. So that whole thing would have vanished.
Right. And then we just had yk prime, and then that would just be that. Good. So it is looking like what we had before, thank you. With the caveat that we now have here this new constant bk prime xk, which you're not going to see initially. These have different degrees. And so this can be a little bit troublesome. Is there a way you could maybe fix things so that they all have the same degree? So running out of space, and of course, this is the danger of writing things on the bottom board. I cannot move this one up easily. Can I erase the wish list for A's now? So it may not be a terrible thing that they're of different degrees. But this is 1 degree lower. Any thoughts as to how we could get everything to be the same degree? I can think of a smart-ass thing to do. So when I was an undergraduate, Peter Jones was an outstanding lecturer at Yale. I was fortunate enough to have him for 3 classes. And he basically said that there are 2 things mathematicians can do. What are the 2 things we can do? You can add 0, and what else can you do? Multiply by 1. And then he pauses, well, the log of 1 is 0, so there's really only one thing you can do in mathematics. You can do nothing. And the whole point of all of this is to try to find ways to do the algebra. Is there anything we could do to this to help?
Multiply by a factor of like x minus, or actually x minus xk plus, yeah, x minus xk plus yk. That way you can force beta 1 to be 0. Beta 1 equals 1.
Okay, so you want to do x minus xk.
Yep. Plus yk. Then when you put in xk, you just get yk, so you can make beta k equals 1.
So if we do that, or do you want to make this maybe 1 instead of yk, so we keep the yk out here?
Or you could do that, yeah.
You know, you've got a couple of ways to do things. Now, the thing you have to be careful about is if you do this either way, when you take derivatives now, this is going to change things.
Yeah, but it'll still vanish. I guess, yeah, then when you do calculations for alpha k, it'll get messed up.
But it's not a bad thing to try. Yes?
You could multiply by x over xk.
So if we multiply by x over xk, we've changed this function, we've changed the degree.
Don't we want to change the degree?
We do, but we have to change it in such a way that we can adjust things a little bit. I don't care about lower order terms. So maybe we change this function a little bit, which leads to a change in ak, but a lower order change in ak, or a lower order change here. And again, this may not work, but this is just something to think about. Instead of x minus xk, what could we put in that's not going to change anything? So as soon as I put in this factor, this is now a factor that's not identically 1. So instead of looking at x minus xk plus 1, what should I try? So you have to be thinking add 0 or multiply by 1. Right now, if you want, we can view this as there's a giant 1 over here. Can you rewrite 1 This is almost good. So we could have 2 different terms. We could have some terms of degree 1 and some terms of degree 0, and maybe things cancel. So I want something that is the same as 1, but has x's in it. So give me something that is 1, but has x's in it that cancel.
X over x? I don't know.
So we could do x over x, but then you have an x in the denominator, and now we don't want to have an x in the denominator. So instead of x over x, what could we do?
X minus x plus 1.
X minus x plus 1. What if we tried something like that? If we have x minus x plus 1, we can write this as x plus 1, minus x. Because bk is a polynomial of degree 2n minus 2, when I multiply by x plus 1, it's a polynomial of degree 2n minus 1. When I multiply by negative x, it's a polynomial of degree minus 1. And so if I try doing that, I would get, I'm going to just look at the k term. I would have yk prime minus yk bk prime of xk. Then it's times ak of x. But we know ak of x was just x minus xk times bk of x. Right? Probably should write this a little bit lower because of how the image is going to be. So we'd have x minus xk bk of x. Now, the negative x times this would give us a negative yk x bk of x, right? And then we'll have plus yk x plus 1 bk of x. So this is almost what we want. Notice that this is almost going to perfectly cancel out maybe what's going on in there. Right? This is enough to at least give us now a representation where everything has the same degree. The question is there a better way of doing this? Instead of having x, I would much rather have x minus xk. Because then I could combine it with the x minus xk over here. And then that would just be my nice polynomial a of x. So if I added, if I subtracted xk here and added that, then I would have a new term coming in there. So I could write this as x minus xk plus xk. And when I do that, the x minus xk part over here, well, now this will be x minus xk times bk of x. That's just the a of x. And then this part over here would just reinforce that one. And I think you would then get, yk prime minus 2 yk ak of x. Sorry. I think like this, right? Oh, no, I dropped the bk prime. So, oh, but that's bk prime, and that's just bk, not bk prime. Never mind. So it combines in a messy way. But it will at least have the ak of x. So you would have yk prime minus yk bk prime of xk minus yk, I think if I've done it right, ak of x. And then the other piece, we have a yk x plus 1 times bk of x, and then we'll have an xk bk of x. So that one would be a little bit more complicated. It would be, yk, everything at least has a yk, which is nice. And so I would have yk xk bk of x.
Everything has a bk too.
I'm sorry?
Everything has a bk too.
It does have a bk as well.
Which is xk plus x plus 1.
Right. But I want to write it like this. There's actually going to be a minus sign here from the minus hitting the xk. So it'd be minus xk bk of x plus x plus 1 bk of x. And I want to write it like that because this is now clearly the higher degree term. And the only thing that bothers you a little bit is this is an x plus 1 rather than an x minus xk. It seems like I would much rather have that as like an x minus xk. But that's not going to be that hard to fix as well. I can just write this as x minus xk plus xk, and so I'd have an xk plus 1 which would come in here. If I have the xk plus 1, the xk plus 1 is going to cancel out the xk over there. And so when the dust settles, you can make this as x minus xk, and I think it's just like this now. I might have made a small algebra mistake at the end. But now this is writing things in a really good way. And if you look at now, everything, this is just going to be our ak of x again. So we now have a representation where we've interpolated using the values of the function and the derivative. We can do it for arbitrary many points. And we have it such that the two polynomials have the same degree. And they have a really nice natural form, and the coefficients come from the values of the function and the derivative. So for the next class, we'll probably talk a little bit, or at least I'll show you how my colleague proved this in his notes. Very, very different approach. What I like about this is we start off with a simple case. We know what's going on in the line. Is that too simple to generalize, or can we actually gain something useful from that and see how to move things? We already had a solution earlier. We didn't have to go to have the stuff at the same degree. I have deliberately not read his notes to try to be in the same mindset as you. I do read a little bit to see where does he want me to get to, so at least I know the formula. And I saw, okay, he seems to care for some reason that they all have the same degree. So can we somehow find a way to do the algebra to get them to be the same degree? And the answer is yes. And we're just constantly adding 0. We didn't really do much multiplying by 1. But this is the hardest part as you go further and further in math, is trying to figure out how do you do the algebra so that at the end of the day, things cancel nicely. All right, so this is a good place to stop. I will stick around in case people have some questions.